So we're coming to just about to the end of the pure geometry part of the course. Geometry is always going to continue to be important, but we're going to combine it more with algebra. We're going to use algebraic tools much more. But there's just one more, just really wonderful idea, set of ideas that have to do with circles that are just too good not to share and really do come up. And that's inscribed angles. And so inscribed angle is when you have a circle, like I've got pictured here, and the vertex of the angle is on the circle, and the sides are chords of the circle. In other words, you can define it by these 3 points, A, B, and C, and everybody's on the circle. And so in particular, nobody's at the center of the circle. So you want to think of this, a very good way to think of this is you're sitting at B and you're sort of looking at this portion of the circle. And of course, that's an arc. I said one part, but really it's an arc of the circle. And from some other, you're at some other point of the circle and you're looking at it. And what we're interested in is how big does it look? Which is, in other words, is how much of an angle is there between these two lines of sight? That's a really good intuition to have for this. And some of the problems in the book actually specifically look at that case where this really is 2 lines of sight from one person. So I want to do just a tiny bit of experimentation to show you that there's something cool going on here. And then I'll prove a special case of the big theorem. I won't prove the general case. And that's, I just want to look at, I want to compare how big this arc looks to the observer at B, that's in other words this angle at B, to how big the arc actually is. And our usual measure of that is we call it the measure of the arc, but I want to recognize that that's exactly the same as the central angle. So we've known for a little while that we call this measure of the arc, the way we actually calculate that is we stand at the center of the circle, which is very natural, and we look at how big it looks from the center. So I've set it up with just about a 90-degree angle. And if that were perfectly 90-degree angle, I think we know what this kind of triangle is. Think about that for a second. What is this kind of triangle? That's a 45, 45, 90 triangle. And so that's a 45-degree angle. So, okay, that's one data point. Let's do this. Okay. So when that central angle is 90 degrees, the inscribed angle is 45 degrees. So now let's use the magic of dynamic geometry software. Notice what happens. If I'm standing at the same point B and I make that arc smaller, in other words, I make the central angle smaller, then the inscribed angle gets smaller. And in particular, if this collapses to 0, then B, the angle at B is 0. So that can be a nice special case. It's kind of an extreme case, but it's worthwhile. 0 gets you to 0. Okay. What if I took it all the way over? Okay. What if this angle gets up towards 180? The central angle is getting towards 180. Notice what's happening to this line BA. It's getting closer and closer to vertical. I know it sort of disappears into itself there, but you can see that that angle is getting very, very close to vertical. Oh, that would be 90. Okay, that's interesting. Well, you know what? If there's a simple pattern to be found, two or three data, especially 3 data points, are often enough to find it. It certainly seems to me like the inscribed angle is trying to be half of the central angle. And let's see, so that would be something, if that were the simple relationship, it would say that as the central angle gets bigger, half of that should get bigger. Okay, that's what's happening. They're both getting bigger simultaneously. And we should always have that the central angle here is bigger than this guy. And that's exactly what we have. So that's not a proof for sure. I'll give a proof in this case in a minute. But it certainly, hopefully, should be plausible that we've got this relationship that the inscribed angle has some simple relation to the central angle, and it certainly looks from this data that it's 1/2. And that's, in fact, the theorem. So let's write that down. Theorem, the inscribed angle. I usually state it as the inscribed angle is exactly 1/2 of the corresponding central angle. But another way to say that, if I can spell it right. The inscribed angle, this is what you see in the book, the inscribed angle is exactly 1/2 of the measure of the arc, and it's we call it the intercepted arc, just the terminology. It's the arc that you're looking at that determines that inscribed angle, okay? So I've got a fairly, well, let me come back to the proof in a second. But let me show you, I kind of looked at a special case here to make everything nice and simple. This is really the more general case. I had one of the parts of that angle, one of the segments of that angle actually going through the center, so it was a diameter. But it's actually much more general than that. This is the general case where I'm at some random point on the circle, here it's F, and I'm looking at this arc between G and E, and I'm looking at the angle here. And so again, you want to think I'm standing at F and I'm sort of looking at like some painted, like a mural on a circular wall or something. And I'm just trying to see how big does that look to me? And the cool thing is, notice what's not happening to that 27.12. It's not changing. I think this is probably the most surprising thing when you first see it. It's that these are all very different geometrical pictures. Here's kind of long and skinny, and here's kind of getting kind of closer to D and E. These aren't similar triangles or anything exactly. But what's staying the same is that angle. And that's almost magical. One way to think about it intuitively is here I'm coming really close to the arc GE and I'm looking at it from really close, but I'm also kind of looking at it edge on. Here I'm really far away, or relatively far away from GE, but I'm looking at it face on. And so those two effects kind of cancel out. And they perfectly cancel out. That's the wild thing, is that it always looks the same size to me. Right? And if you don't like the analogy of lines of sight and how big it looks, you don't have to use that interpretation. And you just have to say, wow, this is really cool. If I move around this circle, that angle stays exactly the same, even though a lot about the picture seems to change. And, of course, we can test our conjecture in this more general setting. Let's see if that angle really is 1/2 of the central angle, in other words, what we call the measure of the arc. Oh, you bet, 27.1-ish, 54.2-ish. It's exactly half. And I can mess with it just a little bit more. Let me sort of move G. Let's say this is like 38-ish. This is now 19-ish. And it doesn't matter where that point is. So it's a very flexible theorem. It's very general. If you have staked out 38 degrees of arc anywhere on a circle, and then you pick any other point on that same circle, absolutely has to be the same circle, then it's going to have half that central angle, or in other words, half the measure of the arc. That's pretty cool. So let me go back. I want to prove this real quick in this very special case. This was the special case where one of the sides of the angle happened to be exactly a diameter. And you can totally prove it in the totally general case, of course. But here it's just pretty easy to prove. What I'm going to do is I'm going to, let me actually go ahead and make this register the angle, show the label here. Okay, so I was kind of hiding that before because I didn't want to make it too obvious what was going on. But again, here we see that 2-to-1 ratio, like 122 to 61, 135 to 67.5. There's that 2-to-1 ratio. And you might want to stop for a second. I'll probably put a little Edpuzzle question in here. Is there some sort of nice triangle here? And is there some other angle that's really easy to see and calculate in this situation? And the answer is this angle OAB is easy O. Well, let me fix that. I don't really want OAB. I did that in the backwards order, so let me just do BAO. That's going to be better. And then let me see if I can just fix that. Okay. So look at what we got here. This is telling us that this angle, 2848, 2848, they're the same. Why would that be? Well, it's a very simple reason. This is a circle, after all. If you're going to prove theorems about a circle, at some point, you're almost certainly going to use the fact that any two radii of a circle are the same distance. That's what makes it a circle. A and B are the same distance from O. Therefore, this triangle AOB is isosceles. Therefore, these two angles, the angle at A and the angle at B, are equal. Okay, so now we just need to remember one other fact. So let's see, this the proof in the special case. We just have to, so what we found is that triangle AOB is isosceles. Therefore, well, that didn't work. Angle OAB is congruent to angle OBA. That's what we're seeing there. And we just have to remember the exterior angle theorem. I know that's a while ago, but what that says is that this angle AOC is going to be, the measure of it, let's be technical, the measure of AOC is exactly the measure of OAB plus the measure of angle OBA. Aha. But wait, those are equal. So that's just 2 times the one we're really interested in, which is OBA. Oh, and we're done. That's it, right? Just solve that for this guy. To divide both sides by 2, in other words. That's just 1/2 of the measure of that central angle. So in this case, it's real easy. And in the more general case where that I was showing over here, it's just it's a little harder, but it's still based. It's actually, you first prove this case first, and you get the whole thing. So that's pretty groovy. So the upshot is that if you compare that inscribed angle and the central angle, just one is 1/2 the other. Another way to say it is you're focusing on the that inscribed arc, and the angle from any other point in the circle, and again, this is the more general case, that makes is 1/2 of the angle you would get if you described it as viewed from the center. I'll do another video, a short video for a couple of special cases and applications.